Welcome to AI Paperslop, the YouTube series where we break down the absolute latest AI and tech research. And to kick things off today, I want you to imagine playing a grueling, 30-move chess game.
Oh yeah, you're sweating over the board, overthinking every single move?
Exactly. You're making these intricate tactical decisions, and then at the very end, someone just walks up and says, "You lost."
Just brutal, no feedback at all.
Right. They don't tell you, that you blundered your knight on move 12. They literally just give you a 0.
Yeah, that's incredibly frustrating.
It really is. And today, we're looking at a breakthrough paper that finally gives AI agents the ability to review their own game tape to solve this exact problem. It's called OPID, On-Policy Skill Distillation for Agentic Reinforcement Learning. And this is by Shua Yang, Jinyang Wu, and a whole team of researchers from Tsinghua University and a few other institutions.
Right, and for the machine learning engineers and researchers tuning in, we need to jump straight into the core insight here. Because outcome-based reinforcement learning, specifically methods like GRPO, has totally become the go-to backbone for training LLM agents right now.
Oh, absolutely. Everyone is using it.
Yeah, but it suffers from this massive flaw, which is sparse trajectory level rewards.
Which means you only get that binary success or failure right at the end of a long sequence.
Exactly. So it gives you absolutely no guidance on any of the intermediate steps. But OPID completely solves this credit assignment bottleneck.
Really? How does it pull that off?
Well, it basically extracts hierarchical hindsight skills directly from the agent's own completed on-policy trajectories. And then it routes those skills back to the agent as dense token-level distillation signals.
Wow, okay, so you don't even need those math at external databases anymore.
Nope. It completely eliminates the need for maintaining expensive external skill libraries, which, as a byproduct, solves the distribution mismatch problem and achieves state-of-the-art sample efficiency on complex benchmarks, like ALFWorld and WebShop.
That is massive. So we're moving away from having to explicitly tell the model where it messed up and instead giving it a mechanism to basically figure it out itself.
Yeah, that's a great way to put it.
But to really grasp why OP is such a paradigm shift, we first need to unpack why that sparse reward problem is so detrimental to long horizon agents in the first place.
Yeah.
I mean, outcome-based methods like GRPO, which is Group Relative Policy Optimization, are so popular right now, mostly because they're critic-free.
Right, exactly. They save just a massive amount of memory and compute. Because with older algorithms, like, say, PPO, you have to maintain an entire separate value model in memory just to estimate the expected return of a state.
Which is a massive headache.
It is. So GRPO bypasses that entirely. It just samples a group of trajectories for the same prompt, sees which one's got the highest reward, and basically pushes the policy to favor those relative winners.
But then you have to consider the environments these agents are actually operating in today.
Yeah.
Like we're talking about embodied household tasks, multi-hop web navigation, or even just interacting with a search engine. In all of these environments, the reward is heavily, heavily delayed.
Oh, totally. It is often just a terminal 0 for a failure or a 1 for a success.
Right. So imagine a 50-step web interaction. The agent might make a brilliant search query on, say, step 3, navigate flawlessly for 20 more steps, and then click the wrong button at the very end.
And boom, the entire trajectory gets slapped with a 0.
Exactly. The algorithm treats that brilliant early search query with the exact same negative pressure as the final misstating click.
Yeah, because in long horizon interactions, that single early mistake, or, a late mistake, it just derails the entire episode. Purely outcome-driven optimization, it provides stable pressure to complete the task overall, sure.
Right.
But it severely lacks fine-grained, decision-level credit assignment. So the model is just left guessing which specific generated tokens actually contributed to the failure.
And for anyone listening who has spent the last 6 months fighting with vector databases, trying to get RG-based skill retrieval to work, you know that the industry has definitely tried to fix this before.
People have tried so many things.
Right. Previous papers have attempted to use self-distillation with natural language skills to give the agent that dense guidance, basically augmenting the training loop with procedural knowledge like behavioral rules or subgoal decompositions.
But the catch is that existing skill condition methods rely almost entirely on external skill libraries or persistent memory banks.
Which is just a nightmare to maintain.
It's awful. That reliance introduces 2 huge headaches for AI researchers. The first is just the sheer engineering overhead. Maintaining a dynamic memory bank requires complex infrastructure just for inserting, refining, deduplicating, and then retrieving the skills.
Yeah, that sounds like a full-time
It
job.
really is.
Yeah.
But the second, and honestly much more severe problem, is distribution mismatch, which inevitably leads to state drift.
Because the retrieve skill is pulling from a database of past experiences that might not perfectly align with the current situation.
Exactly.
It's like handing our chess player from earlier this brilliant pre-written strategy guide for the Sicilian defense, but they are currently stuck in a really messy Queen's Gambit.
Yeah.
The advice is technically sound in a vacuum, but it's completely useless and probably actively harmful for the specific board state they're looking at.
That's a perfect analogy, because even microscopic deviations from the assumed trajectory render an external skill totally unreliable. Like a skill retrieved from an offline dataset might assume the agent has already verified a user's credentials, but the current policy hasn't actually done that yet.
Oh, and then following the retrieve skill blindly just causes the agent to crash.
It completely derails. But OPID bypasses this entirely through its strictly on-policy nature. It looks backward at its own rollouts, which guarantees a perfect state match because the skill is derived from the exact trajectory the agent just experienced.
Right, but recognizing that external libraries fail is kind of the easy part, isn't it?
Well, yeah.
The real engineering hurdle is figuring out how to force the agent to look at its own past mistakes without drifting into a new state. Like, how does it actually turn its own hindsight into a usable rule?
Okay, so here's how the pipeline works. The agent runs its rollouts, interacts with the environment, and gets that final terminal reward. Then OP takes those completed trajectories and hands them over to an analyzer.
And what are they using for the analyzer?
The authors utilized a really strong large language model, specifically GLM 5.2, to act as this analyzer. The analyzer is prompted to review the entire sequence. I'm talking every observation, every action taken, and the final terminal outcome.
Wow, just the whole tape.
Yeah, the whole tape. And from this, it generates a post hoc knowledge representation, but it doesn't just spit out a monolithic block of text. It extracts a hierarchical skill representation. And that is key to addressing the granularity trade-off in decision-making.
Okay, so the granularity trade-off being the difference between needing a general game plan versus needing to know exactly what to do at a split-second bottleneck, right?
Exactly. So let's break down the two complementary levels that OP extracts. The first is the episode-level skill. These are broad, stable summaries of a whole trajectory.
Right.
If the rollout was a success, this captures a global workflow. If it failed, it captures a broad failure avoidance rule.
Got it. Can you give us an example of what that actually looks like?
Yeah, sure. To give a concrete example from the paper's WebShop benchmark, imagine a failed trajectory where the agent keeps trying to buy a product without selecting the color and size first.
Oh, that classic mistake.
Right. So the analyzer reviews this and outputs an episode-level skill that acts as a universal rule for that specific task type. It might read something like, before clicking buy now, you must verify you have selected the required attributes like color and size. It's a very robust global directive.
Okay, that makes total sense. And then we have the second level, which are the step-level skills.
Right.
These are precise, localized pieces of decision knowledge. But unlike the episode-level skills, they're extracted only at sparse critical time steps.
Yeah, returning to our chess analogy, the episode-level skill might be, control the center of the board to limit opponent mobility.
Right.
But the step-level skill is specifically for move 12. It's like, move your bishop to f4 to pin the opponent's knight to their queen. It is hyper-specific to that exact state and observation.
But wait, I have to imagine that if you feed both of those to the model at every single step, you just end up totally confusing it.
Oh, absolutely.
Like if I'm the agent, you're telling me control the center and move the bishop to pin the knight simultaneously on every single turn, I might focus on the micro tactics when I really just need to be developing my pieces, or vice versa.
Yeah.
That might just average out into bad generic moves.
Yeah, your intuition is spot on. And that hypothesis is exactly what the ablation studies in the paper confirmed. Applying the same skills to every single step is highly suboptimal because, episode-level skills are robust but often too coarse when you're at a decisive pivotal state.
Right.
And conversely, step-level skills are incredibly surgical, but they're sparse. They really only apply to a few moments in a long trajectory. So to manage this, OPID uses this really clever critical first routing mechanism.
Okay, so it's less like a generic traffic cop and more like, I don't know, a surgical microscope.
That's exactly it.
Like, By default, you use the naked eye, the episode-level skill, to navigate the room and understand the broad workflow. But when the system flags a critical moment, you flick down the microscope, which is the step-level skill, to make the precise incision, completely ignoring the rest of the room for that one specific step.
Yeah, that is a fantastic visual. And the routing itself operates on a hard mathematical rule based on the analyzer's identification of critical steps.
How does it define critical?
Well, the analyzer flags certain time steps as pivotal bottlenecks, and they cap this, by the way, at 5 steps for ALFWorld or just 2 steps for search-based QA.
Oh, so it's very strict.
Very strict. If the current time step is flagged as critical, OPID feeds only the step-level skill to the agent. If it's a normal, non-critical step, the agent receives only the episode-level skill. The two are literally never mixed in the same context window.
Which keeps the context clean and hyper-focused. And the ablation data really proves how vital this separation is, because when the researchers tried superimposing both the episode level and step level skills simultaneously, without the critical first routing performance just dropped significantly.
Yeah, the numbers don't lie. On the ALFWorld benchmark, using the critical first routing achieved an average success rate of 84.3. But when they removed the routing and just mixed the skills together in the prompt, performance plummeted to 77.5.
Wow, a 6.8-point drop. That illustrates exactly what happens when the microscope is permanently glued to the agent's eyes. It just loses the forest for the trees.
Precisely. And furthermore, the authors ablated removing either level entirely just to see what would happen. Stripping away the episode level skills dropped the ALFWorld score from 84.3 down to 74.1.
Ouch.
And removing the step level skills dropped to 79.1. So this mathematical breakdown just definitively proves the two levels are perfectly complementary. You absolutely need the broad workflow for general navigation, and you need the surgical precision for the bottlenecks.
Okay, so now we get to the core of the implementation. Because we have this beautifully routed, perfectly timed natural language skill, the agent knows exactly what textual advice to look at for a given time step. But how does this text-based skill get mathematically converted into an actual weight update for the RL policy?
Yeah, this is where OPID's skill-based self-distillation comes in.
Right.
The conversion from natural language hindsight into a mathematical gradient relies on this brilliant paired scoring mechanism to generate a dense token-level advantage.
Let me make sure I am visualizing this dual scoring process correctly, because I feel like this is where the real magic happens.
That's where.
So OPD takes the routed skill and injects it into the interaction history. So now we actually have two separate contexts. The original context the agent actually saw during its blind rollout, and this new skill-augmented context.
Yeah.
And the agent already generated a sequence of tokens during that blind rollout. So now we ask the old policy to score the exact same sampled response twice, once under the original context and once under the skill-augmented context.
Exactly. The original response the agent generated isn't changed at all. We are simply querying the model's logits to ask it, hey, if I had given you this hindsight skill before you made your decision, how much more or less likely would you have been to generate this exact sequence of tokens?
That is so clever. And that difference in probability is the actual mathematical engine here, right? You take the difference in the log probability between these two contexts, and this difference creates the token-level skill advantage.
Yeah, a concrete example usually helps clarify the math here. Let's say the log probability of the agent generating the token click under the original context was, say, negative 2.0.
Yeah.
But under the skill-augmented context, the log probability of click becomes negative 0.5. So the difference is a positive 1.5. This positive advantage mathematically signifies that the generated token aligns perfectly with the hindsight skill.
And if it went the other way?
Right. If the skill-conditioned context assigns a lower probability to the token, the advantage is negative, which mathematically punishes a token that contradicts the hindsight advice.
Wow. So instead of just a binary 1 or 0 at the very end of a 50-step episode, every single token in the generated response gets a highly specific positive or negative score based on whether it agreed with the hindsight skill.
Exactly.
That is just an incredible density of supervision.
It's massive. And this dense token-level skill advantage is then mathematically multiplied by a weighting coefficient and added to the standard group relative outcome advantage, which is just the normal GRPO signal.
Oh, I see.
Yeah, this additive structure preserves the outcome-based RL as the primary training objective. That ensures the agent still fundamentally cares about completing the task, but it shapes the learning landscape token by token with a hindsight signal.
So the final equation is beautifully simple then. Final advantage equals the episode advantage plus a weighted skill advantage. But there is a fascinating theoretical property hidden in the paper's appendix about this exact equation. The authors provide a formal mathematical proof showing what happens when the standard RL signal completely fails. They mention that the unclipped OPID skill loss acts as a relative KL surrogate.
Yeah, no.
Hold on, relative KL surrogate is a bit dense. Are you basically saying it measures the distance between the model's blind guess and its hindsight guided guess and uses that gap to learn, even if the actual environment reward is 0?
That is the perfect plain English translation. Like, think about a situation where the reward variance in a batch is literally 0. If you sample 10 trajectories for a highly complex prompt and every single one of them fails, getting a reward of 0 standard GRPO breaks down completely.
Right, because there's no signal.
Exactly. The group relative advantage becomes 0 for all of them, meaning the gradients vanish and no learning happens at all. The model just stalls out entirely.
But with OPID, Corollary 3 in the paper proves that even if all trajectories in a batch tie for the same reward, basically zeroing out the episode advantage entirely, the skill advantage remains active.
Yes.
As long as the skill-augmented context produces a different log probability than the original context, you still get a non-degenerate token-level learning signal.
Which means the model can still learn how to behave better from its own hindsight, even if every single rollout in the batch was a catastrophic failure.
That's wild.
It really is. It learns from the delta between its blind self and its hindsight-guided self. So it continues to align its internal weights with the failure avoidance rules it extracted, basically preventing the training process from stalling out on incredibly hard tasks where initial success rates are near 0.
Okay, so let's look at the actual empirical results to see if all this beautiful mathematical theory actually holds up in practice. How did it perform on embodied reasoning tasks like ALFWorld, which require navigating a text-based virtual house and finding objects?
So, using the Quen 2.57b instruct model, OPID hit a 90.0 average success rate. And to put that in context, the strongest hybrid baseline was sitting at 88.3.
That's a solid jump. And on WebShop, which is this complex web navigation environment where the agent has to search for and buy specific products based on really intricate user instructions, they tested a much smaller model, right? Quen 3 1.7b.
Yep.
And OPID achieved a 64.8 success rate there, while the closest baseline only managed 58.6. I mean, beating the best competing method by over 6 points on a 1.7 billion parameter model is no small feat.
Oh, totally. And they also saw consistent improvements across both the 3 billion and 7 billion Quen 2.5 backbones on search-based QA, which involves interacting with a search engine to answer multi-hop questions.
Wow. But beyond the raw performance ceilings, the sample efficiency data is what is really going to catch the eye of anyone paying for the compute to train these models.
Yeah, that compute bill is no joke.
Exactly. Because generating rollout data in simulators like ALFWorld is incredibly slow and computationally expensive. But in their ablation studies, the researchers tested how the models performed when restricted to only a fraction of the training data.
Doing more with less.
Exactly. What were the exact data fraction numbers again?
So OPID, using just 60% of the training data, achieved a 71.9 success rate on ALFWorld.
Unbelievable.
Right. This drastically outperformed the baseline GRPO using 100% of the data, which only achieved a 58.6 success rate.
I just need to let that sink in for a second. OPID, with nearly half the environmental interactions, beats standard GRPO with the full data set by over 13 points.
Yeah.
And that's because OPID extracts hierarchical hindsight skills, so it squeezes exponentially more supervision out of every single trajectory. Standard GRPO looks at a rollout and extracts just a single bit of information. Success or failure.
Just a 1 or a 0?
Right. While OPID looks at the exact same rollout, extracts a global workflow, identifies critical bottlenecks, generates localized decision rules, and turns all of that into dense token-level gradients.
And that's why making outcome-based RL far less dependent on massive numbers of environment interactions is so important. It drastically lowers the barrier to entry for training capable agents in slow or expensive simulation environments.
But, whenever a model is this sample efficient and learns this aggressively from its own data, the immediate worry is always overfitting. Is the agent just memorizing the training data because the token-level distillation signal is so overwhelmingly strong?
It's a fair question, but the cross-domain generalization tests address that concern directly. The researchers evaluated OPID on the ALFWorld unseen split, which actually contains environments and object configurations the model had never encountered during training.
Oh, okay. So if it had just memorized the layout of the training rooms, its performance would absolutely crater here.
Exactly. But instead, on the unseen split, OPID improved the average success rate by 7.7 points over standard GRPO. Wow.
So the distilled workflows, like the episode-level rules about how to systematically search a room, or the step-level rules about how to properly interact with a novel object like a sink basin, they actually transfer to new configurations. The agent is internalizing true, generalizable skills, not just memorizing specific item locations.
Man, this deep dive into the source material really highlights a major paradigm shift for the field. We are moving away from viewing agent trajectories merely as raw data points that yield a binary reward to treating them as rich, reusable records of decision knowledge.
Yeah, OPD proves that we can mine the model's own experiences on policy, route that knowledge intelligently based on the granularity of the current time step, and just internalize it directly into the network weights.
No database required.
Right. We don't need to bolt on external skill libraries or build complex vector databases to retrieve privileged context at inference time. The intelligence becomes entirely self-contained within the policy itself. Which leads to a really provocative thought to leave you all with today. I mean, if models can successfully extract, route, and internalize their own hierarchical skills purely from hindsight, could this recursive self-improvement loop eventually eliminate the need for human-authored system prompts or standard operating procedures entirely?
Oh, that's an interesting thought.
Right. If an agent can identify its own failure modes and permanently patch its own policy via self-distillation, do we even need to explicitly tell it how to act anymore? Or will it just figure out the optimal workflow completely on its own?
I mean, the capacity for models to self-correct and distill their own procedural knowledge on policy really suggests that the limit of recursive self-improvement is much, much further out than we previously thought.
It's definitely a lot to think about for your own ML workflows. Remember that 30-move chess game we talked about on the start? With OPID, the agent isn't just told it lost anymore. It basically acts like a grandmaster reviewing their own game tape.
Yeah, exactly.
It sits down after the match, reviews the board, realizes exactly why move 12 was a total disaster, rewrites its internal understanding of the state, and then never makes that blunder again.
Thank you for joining us on this deep dive on AI Paper Slop. We will catch you next time.